Scantegrity II, end-to-end verifiability for optical scan election systems using invisible ink confirmation codes by David Chaum, Richard Carback and Aleks Sherman of University of Maryland, Baltimore County, Jeremy Clark of the University of Waterloo, Stefan Popoveniuc of George Washington University, Ron Rivest and Emily Shen of MIT, Peter Ryan of Newcastle University, and I'm Aleks Essex of the University of Ottawa. This is the online version of the original talk which we gave at EVT July 29, 2008. There is a way to take the most popular voting system in America today, optical scan, and give to it the highest level of election integrity known. But not only this, we can do so in a way in which the equipment stays the same. The election procedures stay the same. And finally, voters vote the same. Scantegrity II allows end-to-end verifiability as an option for voters. It preserves privacy, it preserves procedures, and it preserves reliability of the underlying optical scan system. It has a practical and low-cost implementation. We're going to talk about Scantegrity II, but first, let's frame this discussion with what we already know. The mechanics of a voting system can be broken, roughly, into two steps. You cast your ballot into a collection of ballots, and you count that collection. Well, let's talk about election verification. How do you know the election was run properly? You need a verification mechanism. Well, what do we use today? We use paper. How? As we saw with voting, paper-based verification can also be broken into two steps: casting and counting. Verifying casting means that you as a voter witness the mark that you make be contributed into a collection of ballots. In this case, your ballot passes through a scanner into a ballot box. We call this collected as cast. On the other side of the coin, verifying the counting means that you as a voter can witness, via a manual recount, the collection of ballots being counted. We call this counted as collected. Putting this all together gives you counted as cast, right? Wrong. A degree of verification, by which we mean one stretching from you the voter all the way to the next president, must require that these two verification steps be performed on the same collection. But between the time you mark your ballot and the time a recount may or may not occur, things can happen. Fraud, errors, undetectable bad things. So it can be said that voting today is missing a big link in the chain. What we're presenting is an add-on to today's optical scan system that provides this missing link, an unbroken chain from end to end, and it's called Scantegrity II. I'm going to begin by showing you how you vote and how you as a voter can verify that your vote made it into the tally. I'm going to talk about some of the major points of discussion that this proposal brings about, and finally some of the things that we've done with this technology to date. Let's begin with what the voter sees. I want to vote. I check in at my local polling place and am presented a ballot. It looks just like an optical scan ballot. I go to the booth. I mark the ballot. The bubble I mark darkens, but oh, hey, a confirmation code appeared in the bubble. Cool. Don't worry, the optical scanner won't notice. Just hang on to this for a moment. We're going to talk about it. My ballot gets scanned by an optical scanner. I get my I voted sticker, and I'm done. That's all there is to the voting process. But maybe I'm that small percent of folks who say, hey, I'm not satisfied with that missing link in the verification chain we were talking about. I want something more. I want to see my vote make it all the way to the tally. As you noticed, a confirmation code appeared when we marked the bubble. It was printed in invisible ink. Okay, so all I do is write down the code. On this ballot, the confirmation code of my selection is VX, so I write down VX. and I'm going to take that code home with me. I save that little scrap of paper for later. Then I take my ballot to the scanner. I get my sticker, and I go home. So, what do the election administrators do? Well, not that much new, really. The officials get the results from the scanners in the same way they're accustomed to. They also file the forms and archive the paper trail as they normally would. However, they do post these confirmation codes online. After the election has concluded and the codes have been posted online, I can take that little slip of paper that I wrote down my confirmation code and I can look it up on the website. Again, my code was VX and the website displays VX. I've verified my receipt was collected as cast. You know, maybe I can get a sticker for this too. So that's what the voter saw, but let's put this all together. Through the receipt checking step, the voters are vetting an online collection. This vetted data is run through a special backend to produce a verifiable election outcome. It uses this vetted list to produce a verifiable total in a way that doesn't reveal who voted for whom. That's all the backend does. In addition, this outcome can be compared to the optical scanner's outcome. But because the data came directly from the scanner, it will always match the scanner's total, unless of course some fraud or other error occurred. Note that although a scanning error won't cause a difference in the tallies, it will be detectable through the voter's receipt. The codes won't match. So what about this back end? The back end anonymizes the individual data and produces a verifiable total. There are numerous ways that this can be implemented, and many proposals have been made across many years of literature. Some of these proposals use cryptography. Others use nothing more complicated than a pen and paper. But for practical systems, you would want to use cryptography. It works in the same way. This is what we call end-to-end verification. This means that the collected as cast verification step and the tallied as collected verification step are both performed on the same collection of data. And we did this all in a way that doesn't reveal who voted for whom. This is the Scantegrity II approach. But it does raise several questions in the minds of voters, a few of which, the more common ones, we're going to address right here in this presentation. First of all, does the receipt show how I voted? The answer is no. All of the codes on your ballot are randomly assigned. In addition, each serial number has a totally independent random code assigned to it. That means that if you mark the first person and receive a confirmation code, and someone else that you know also marked the first person and received a confirmation code, your respective confirmation codes will be different. In addition, someone seeing the confirmation code that you wrote down does not give them any information about who you voted for. Well, what happens in the situation when I write down a code and I check it online and the code that the website displays is different than the one I wrote down? Well, if the receipt that I wrote down doesn't match the public record, I as a voter can file a dispute. Knowledge of a valid code for a particular contest is probabilistic evidence that a particular code was voted for. That means to be successful in my dispute, I have to give them a valid code. But because I as a voter can't see the codes initially, then all I can do is either give them a code that I really did see or try to guess one up. Additionally, the election authority can exercise a proof to show what the valid codes were on the ballot. In Scantegrity I, all of the codes were visible. So proving that I as a voter chose a particular code required pulling out the physical paper ballot. This required a complicated procedure to conduct this proof while protecting voter privacy. In Scantegrity II, the unmarked codes are hidden, and so in this way, the dispute resolution process can be transitioned from an in-person performance to an automated online mechanism. But if I can't see the confirmation codes until I mark them, then how do I as a voter know that they were printed on my ballot correctly? Well, when I'm at the polling place, but before I vote, I can request an additional ballot to audit the printing of. This would involve me filling in all of the optical scan bubbles to reveal all of the confirmation codes. I can take this home with me, and when I go to check the confirmation code that I voted for, I can also check these confirmation codes as well to make sure that everything matches up correctly. Finally, and in many ways most importantly, comes the question of, well, don't I need a PhD to understand Scantegrity II and how it works? As far as I'm concerned, no. Think about it. What are we asking the voter to do? Well, the core voter verification steps are simply to write down a confirmation code and then look it up on a website. I think it's quite obvious that you don't need a PhD to perform this step. If you've ever rented a car or booked a hotel room, you've been given a confirmation code which you've used to later verify your booking. Well, then you might say, well, doesn't this back end use cryptography? Well, yes it can. It doesn't have to, remember, and in fact there are proposals out there to implement this back end using paper and pencils, and no math and no computers. But it does speed things up when you use computers, because you can click a single button to perform all of these steps and check the tally of an entire election in a few seconds. This software tool is open source and implemented from an open specification. Anyone can write a software tool, and anyone can run any number of the software tools that would be available. The fact is, the voters themselves do not need to run this step if they are willing to delegate it to someone else they trust, such as a democracy watchdog group. If you are interested in learning how this tally verification step works in a way that doesn't use mathematics or cryptography, I would point you to the paper I presented 1 week previously at Workshop on Trustworthy Elections, entitled Aperio, High Integrity Elections for Developing Countries. This system highlights this step using nothing more than basic office supplies. What about implementation? Scantegrity II was implemented in Java and runs off the codebase of its predecessor, PunchScan. It's open source and employs a particularly efficient construction, allowing one to process a large-scale election and verify it in the order of minutes. This contrasts favorably with other implementations of other systems which may produce a verification of an election outcome on the order of weeks and months. To highlight the success and evolution of this project, we point your attention to several elections that we've run, beginning with PunchScan, then Scantegrity I, and now Scantegrity II. Some of these elections were binding, with sizes ranging up to the hundreds of voters. With respect to cost, the back-of-the-envelope calculations that we've performed based on our own printing costs of Scantegrity II ballots show that they compare favorably to optical scan ballot printing. We ourselves have been able to print Scantegrity II ballot prototypes for below the 50-cent to $1 unit cost of conventional optical scan ballots. And speaking of printing, let's take a look at the finished product. Here is an unmarked Scantegrity II optical scan bubble. Here it is again when it's been marked by the special pen. You can see that the bubble has darkened and the confirmation code OU has been revealed. In conclusion, Scantegrity II provides universal voter verifiable election integrity in a way that's easy to use. You mark the ballot the same way hundreds of millions of Americans already do, and because it's an add-on to the process, it won't significantly change the equipment or procedural needs that the thousands of optical scan precincts already have. This project has evolved through research and testing to the point where we feel it's ready to begin trials in public sector elections. For more information about Scantegrity II, visit scantegrity.org and read the paper. Thank you for listening, and happy voting!